Hello, I am Manabu Tsukada from the University of Tokyo. In this presentation, I will be presenting roadside-assisted cooperative planning using future path sharing for autonomous driving at VTC 2021-Fall. The background of this research is Connected, Cooperative and Automated Mobility (CCAM) initiative in Europe and Connected and Automated Vehicle (CAV) initiative in US. Both show that communication and networking are important for safety and efficiency for self-driving cars. The figure shows the roadmap of the European Commission for Connected, Cooperative and Automated Mobility. First of all, the functions of CCAM are categorized into Day 1 to Day 4 functions. In the cooperative ITS, I share where I am and what I hear is defined as a message for sharing vehicle information, traffic congestion, and accident information. These messages, such as cooperative awareness message and decentralized environmental notification message, has been standardized and are expected to be widely used around this year. On the other hand, sensor data sharing is being discussed as Day 2 feature. I share what I see. There are discussions for standardization of this feature as a collective perception message has begun. Drafting of technical specification and technical report has begun. The roadmap shows the deployment of Day 2 by 2025. Day 3, we share our intentions. The corresponding feature is future path sharing. We will discuss it later. Day 4, future mobility, is shown as we coordinate all maneuvers. The draft of the technical report on maneuver coordination message (MCM) has been written. This research aims to support the function of automated vehicles in cooperative mode using VTX. In particular, this research aims to enhance prediction and planning with VTX and implement and evaluate them in real automated driving software. As far as we know, AutoWare and Baidu Apollo are the only open source automated driving software. In this research, we will use AutoWare. The diagram below shows the function of automated vehicles and cooperative driving. Autonomous vehicles in general, including AutoWare, use map and sensors as input and proceed through the process of perception, prediction, and planning and control. On the other hand, as you can see in the previous slide, research on cooperative perception using VTX has emerged. Our research presented at last year's VTC was also an extension of AutoWare to achieve cooperative perception. In this research, prediction and planning will be supported and enhanced by VTX. Prediction and planning need to deal with future data, while perception exchange real-time information. Therefore, we will support automated driving with future path sharing and cooperative planning. For cooperative planning, we need to exchange future data. This is because today's cooperative ITS standards exchange real-time information, and there is no future data. Two representation formats can be used for represent and coordinate future data, grid-based and path-based, as shown in the following paper. At the last year's VTC, an optional field called Path Future was proposed to extend the cooperative awareness message. Also, in the research of maneuver coordination, a path-based future information exchange called planned trajectory was proposed. The research on the bottom right is the maneuver coordination research we presented at ITSC in this month. which also extend hardware. The contribution of this study is designing a roadside unit that enhances vehicle prediction and planning cooperatively with other vehicles to improve traffic flow at intersections. The proposed method is divided into two schemes: a periodic message broadcast to exchange vehicles' future paths, we call it future path sharing, and a maneuver coordination algorithm based on a reservation table that manages a set of future paths in the RSU we call cooperative planning. We implemented the solution in hardware. To the best of our knowledge, this study is the first for implementing cooperative planning in hardware. For the future path sharing, first we convert the trajectory to the future path. The trajectory consists of continuous paired sequences of location and velocity. The future path consists of continuous pair of sequences of location and time. The future path employs a data structure that makes it easy for car and RSU to detect conflicts. The receiving vehicle can treat the received information as a dynamic obstacle by integrating it with the output of perception module. This integration potentially causes unnecessary deceleration because the future path is treated as a future obstacle. When the RSU receives the vehicle's future passes and it updates its reservation table, the reservation table is the RSU's database that stores the set of future passes sent by autonomous vehicles. When a received future path conflict with another path in the table, the RSU sends the initiation message to a vehicle to enter a coordinated mode. Our scheme is a hybrid one in which vehicle create a trajectory and the RSU modifies their speed along the trajectories. An autonomous path is calculated by autonomous vehicle to the desired destination. The coordinated path is a new path in which the RSU modifies the autonomous path to avoid conflict and improve traffic flow. We implemented the proposed method by extending hardware. This figure shows the system design. Hardware provides a set of functionality necessary for autonomous driving, including localization, perception, planning, and control. First, the trajectory sent from the planning module to control module is converted into a future path and broadcasted 10 times per second via UDP. On the receiving side, the future path is merged with the result of perception. If this is the case, the future path will be recognized as a future obstacle and unnecessary slowdown will occur. Therefore, RSU generate the conflict-free path and perform coordination. Hardware planning module is divided into three parts: mission planning, scenario selection, and behavior planning. The mission planner calculates the entire route to the goal by searching a static map. A scenario selector decides which behavior planner should be applied depending on the situation. Currently, hardware provides two modules, one for on-road driving and another for parking. We do not use parking module, and lane driving module generates the autonomous path and send it to RSU by UDP at 10 Hz. Then RSU modify the speed of the path and return as a coordinated. Here is an overview of our implementation. The white box comes with hardware, and blue box is newly implemented in our extension. The detail is in the paper. Our extension is related to cooperative mode and a new behavior planner in vehicle side called coordinated planner. The RSU side, in addition to cooperative mode, we added a reservation table conflict detector, and velocity. Here is a flowchart, and the detail is in the paper. The RSU apply one of three modes for each vehicle as follows. Auto is used when the vehicle follows autonomous planning. C-slow is used during coordinated mode while slow down, and C-fast is used during the coordinated mode while speeding up. Fast of the vehicle is auto, and if there is a collision, it goes to a C-slow. And if there is no collision, RSU search for the room for acceleration. And if there is a room for acceleration, it accelerates. If not, it stays auto. In the evaluation, three personal computers representing car A, car B, and RSU are connected to LGSVL simulator. A wired network connected the three PC. We choose a blind intersection pre-installed with LGSVL. We set the starting and destination point so that car A would pass through the intersection before car B in standalone mode, as shown in the figure. We visualize a stationary vehicle as RSU. We evaluated the following scenarios: standalone without communication, future path only, autonomous vehicle broadcast the future path by B2B, future path with RSU as our proposal. We conducted 10 simulation experiments for each of these scenarios using same starting point and destinations. The figure shows the speed of the two vehicles near the intersection. Green is the result of car A and orange for car B, and the larger value indicates the direction of travel. In the standalone scenario, car B always stopped at 5 meters before the intersection for car A passing first. In the future path only scenario, car A and car B recognized each other. They slowed sooner within 20 meters from the intersection. The figure C shows that both car A and car B did not stop before the intersection using our proposal. Tables show all the results and passing times. The standalone case, car A traversed the intersection first all the time, as designed. On the other hand, car A traversed the first 6 times in the future path only scenario, 4 times for the future path with RSU. Figure shows the passing time of 10 trials and their variations. The future path only scenario slightly increased the average passing time for 2% because the vehicle slows sooner than in the standalone, as shown in the previous slide. Our proposal successfully reduced the average passing time about 10 seconds, representing a 20% improvement. The coordinated path of the RSU effectively avoided the conflict and improved flow. In conclusion, this study proposed a method for cooperative path planning using future path sharing. Our proposition by extending auto-aware is evaluated the LGSVL autonomous driving simulator. Our proposal effectively coordinate vehicle speeds and achieve a 26% faster travel time for both vehicles through the intersection. For future works, we used a wired network in this study. However, we plan to use a wireless network or a network simulator in the future. Furthermore, field experiment would provide a more realistic environment for evaluation. The proposed scheme can be extended to the mixed traffic stream with non-connected cars and vulnerable road users. The evaluation for the scenario is future work. Thank you for listening.